This lesson is going to talk a little bit about our chapter in organic chemistry called Families of Carbon Compounds. So we're going to look at functional groups, the intermolecular forces between functional groups and intermolecular attractions in general, and then a tool used to identify specific functional groups in molecular compounds known as infrared spectroscopy. So through a process of a really good group work, you're going to tackle teaching one another major functional groups, that correlation between the properties of functional groups and molecular compounds and their intermolecular forces. And finally, the chapter wraps up by sharing with us a lab tool called infrared or IR spectroscopy, in which we're able to identify functional groups that are present in a molecule. The team will begin looking at the backbone of all of organic compounds, known as the hydrocarbon. The hydrocarbons are alkanes, alkenes, alkynes, and the aromatic compounds. In the first section, we learn how to define a hydrocarbon. We look at the families that belong in that group called ane, ene, ine, and aromatics. We recognize the line bond formula for each of their molecular geometry. We become familiar with the term saturated and unsaturated, and look at the molecular structure for the molecule known as benzene, the aromatic compound. This is an entire chapter later on in life in organic chemistry, but we introduce the molecule to you right now, kind of get you thinking about the term aromatic. I'd like to introduce the term hydrocarbon, that backbone of chemical compounds in the organic family. Of course, they contain carbon and hydrogen, a hydrocarbon, the two essential elements. The first of these hydrocarbons, as I mentioned, is an ANE, an alkane. Hydrocarbons that do not have multiple bonds between carbon atoms. Another way of saying that is all single bonds in the molecule. The general formula for ANE is CnH2n plus 2. Now let's make sense of that. Alkane, CnH2n plus 2. Here's our first example. This molecule is called pentane, and look at why. When we look at pentane, I have 1, 2, 3, 4, 5 carbon atoms. The prefix represents pent. P-E-N-T, pentagon, for instance, represents 5. And now notice the ending to represent all single bonds in that molecule, A-N-E. There are no double or triple bonds. Think about the number of hydrogens on this molecule. The terminal hydrogens have the terminal carbons have 3 hydrogens to complete their octet. The interior carbons each have 2 hydrogens to complete their octet. Count them with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. C5, the value 10, 8, 12. That's 10 plus 2 times 5 is 10. 2 more, and the reason we're adding 2 more because we're terminating the chain and need to saturate that compound's valence electrons by adding 2 more hydrogens. That's the plus 2s, those carbons at the end. C5H12. Now notice this is a linear understatement, so there's nothing molecules up, down, up, based on the sp3 hydrogen for 9 degrees. There's nothing straight about it, but it is a straight chain. There's no branches, there's no cyclic structures, so we call that a straight chain. Now look at this prefix, cyclo. Notice how we've taken the terminal ends of a straight chain and we want to connect with each other. This is a prefix hex, hexa, which means, and the prefix, suffix, the ending, is ane. It means all bonds. Now with me, we have 1, 2, 3, 4, 5, 6. There's the part of the word. It's in a cyclic structure. That's the cyclo part. And I see the prefix ane, meaning single bonds. How many hydrogens do you count now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5, 8, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5H12 in a cyclic structure. Let's write those formulas and names for the first 10 alkanes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I just wanted to check that math. All right, methane is CH4, straight carbon or hydrogens, methane. Ethane, C2H double plus 2 is 6. 6, that's ethane. C3H8, propane. 3 all single bonds, 8 hydrogens to satisfy the octet. Butane, C4, 10. 4 carbons, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Pentane, C5, H12, pentane. 5 interior would have 2 hydrogens. Thinking about what you see, H3, 1, 2, 3 times, and a CH. It's another way to show that. Here's hexane, C14, heptane, C7, 14, 16, octane, C8, H18, nonane, C9, 8, decane, C10, H22, following the same trend of how you would draw the molecular structure. So for instance, decane terminal, CH3, you have carbons in the chain to another terminal, CH3, a total of 10 carbons. These are all known as all bonds, so you see every single time the A-N-E ending. If we do have a multiple bond, we change the ending to let the reader know if it's double or triple. If it's a double bond, we have an E-N-E ending known as an alkene. Notice here we have 1, 2, 3 carbons. There's a prop to represent 3. We could have propane like the previous page, but notice we have a different ending to know that the now had I drawn the picture the same way, actually the same molecule, we're just counting from the other direction. The carbon that starts the double bond gets the priority in the numbering system. Carbon 1 to 2 into the double bond. Carbon 2 to 3 is a single bond. So that it's one segment. We just flip the molecule in space. Here we have cyclohexene. 1, 2, 3, 4, 5, 6. There's the hex for hexa, the 6 carbon. It's a ring structure, so there's the cyclo. And letting you know there's a double bond is E-N-E. The double bond that starts, as a carbon that starts the double bond, is the priority when you know cyclic structure. So the double bond exists between carbon 1 and 2. And I don't care where I rotate that double bond to. Let's say I place it here. It's still the same structure because it's still carbon 1, 2, 3, 4. Cyclohexene. What would you think 1 butene and 2 butene might look like? Well, what prefix but stand for? That's for ene, says it's a double bond, and carbon number 1 is going to be the origin of the double bond. 1 between carbon 1 and 2, we contain the double bond, so we show it like this. And if you see 2 butene, 1, 2, telling us the order of the double bond will be between carbon 2 and carbon 3. That's a double bond. So we have a double bond making that particular molecule sp2 hybridized, planar. So again, 1 domain, 2 domain, 3 domain with your terminal or you see 4 domain 3 hybridization. And so you've just moved the of the pi bond to show that with the numbering system to let you know the carbon that originates the double bond. And that's what we drew, 1 butene and 2 butene. Propene, CH3, CH, CH2 is an alkene. Write the structure of a constitutional isomer of propene that is not an alkene. It does not contain a double bond. So the CH3, let's find the formula we have. 1, 2, 3 carbons, 3, 4, 5, 6 hydrogens. How else can we arrange those and still satisfy? And I'm going to think molecular structure. 1, 2, 3, 4, 5, 6 hydrogens. I satisfied that molecular formula. Remember, these are called constitutional isomers. This is propene. This is cyclopropane, constitutional isomers. Let's introduce YNE, alkyne. And of course, this is going to contain a triple bond. Now, all of a sudden, notice that one has SE hybridization. That means it's linear. 30 degrees is its bond angle. So we have a very flat structure. Carbon 1, carbon 2, carbon 3, 5. So we go back to sp3 hybridization, 3, 4, and 5. But it makes a very linear molecule. Here's ethine. We have a triple bond between the 2 carbons. Each of the prefix 2 carbons, ethine. This structure has 5 carbons. That's where you see pent. And I'm letting you know the location of that triple bond with the numbering system. The triple bond is between carbon 1 and 2, so 1 pentyne. If we move the triple bond, we want to make sure that we give it the lowest number possible. The structure, by numbering from right to left, come up with a 2 pentyne name. What would be incorrect is to number from right. It would end up on carbon 3 pentyne. And if I numbered in the other direction, and the rule says, pick the direction that gives that triple bond the lowest number. That's the priority there. So always check the direction you should number when you're naming these compounds. Make sure you start from the side that gives the lowest number to the origin of the multiple bond. These are aromatic compounds we'll need to know. Aromatic. Well, they contain a special type of ring. That most common example is a benzene ring. Notice how we have alternating double, single bonds in a cyclic structure. There are 6 carbon rings, 1, 2, 3, 4, 5, 6 hydrogens in a benzene ring. So our formula for benzene is 6. I can see that we can resonate and move double bonds to create a stable resonance structure where double, single bond alternate in this fashion, double, double. And so these two structures exhibit resonance, the alternating double single bond, which means that it's not really a single bond, it's not really a double bond. It exhibits resonance. Those pi bonds are to be delocalized, if I can spell that. Delocalized. The benzene ring, draw the circle inside to remind you that the pi bonds are delocalized. It's a representation of both of these structures. Benzene. C6H6. Another type of aromatic compound puts a methyl group of benzene. Now we name this as toluene. Memorize. If you see a functional group, carboxylic, I'm reading it Q, it has acidic proton on a carboxylic acid, C-OOH. Q, carboxylic acid functional group. If it's attached to a benzene, we name that acid as benzoic acid. Let's memorize these compounds as we move forward. The term saturated compound belongs to the family of alkanes. They only contain single bonds. A molecule is saturated if it's holding as many hydrogens as the carbon possibly can to fill the octet. All single bonds. The molecule is considered to be unsaturated if it has any pi bonds. So alkenes and alkynes, with aromatic compounds, contain pi bonds and therefore are unsaturated. They possess fewer than the maximum number of hydrogens. So when I go from bonds, A, N, E, we see that we're holding the maximum hydrogen possible. To make room for a double bond, we actually have to leave on those hydrogens up with an unsaturated compound here. Remember, C2H4 is the general formula, and that's an unsaturated compound. And with the ending now is on, we had to remove more hydrogens to make room for the triple bond. C2, general formula, we got to get rid of 2 H's to make the triple bond. It's unsaturated. All the octet carbon are filled with H's. If you start removing any hydrogens to create spaces for multiple bonds, the molecule is now unsaturated. Let's begin. If you're watching from home, try this with me, and if we're in class, you'll turn this in on a piece of paper. What are 2 constitutional isomers of cyclopentene that do not contain a ring? Cyclo, the carbons are going to be in a cyclic structure. Pent, that means there's 5 carbons. And ene means that there's a double bond. So we're going to structure with 5 carbons. 1, 2, 5 is in a circle. Because of the prefix cyclo tells me that it's a cyclic structure, not a straight chain, but the terminal ends have connected together to make a cyclic ring. The ENE tells me there's a double bond in that structure. Doesn't matter where, because this will always tell me the origin of the bond. If there's just one double bond in that structure, it's always going to be called carbon 1. So we can leave off the 1 because we know that will be the priority carbon, cyclopentene. We have 5. How many hydrogens are on there? I have 1 more here, 1 more here to complete the octet. Now I need 2 on the remaining carbons. So 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. I count right. 1, 2, 3, 4, 5, 6, 7, 8. How can we arrange 5 carbons and 8 hydrogens to create another type of compound that's not a cyclic structure? Well, if it's not another, I'll draw a line. 1, 2, 4, 5. 1, 2, 3, 4, 5, 6, just as an idea. Fill the terminal N. I have 2 more hydrogens to place. We could fill one of those carbons, 7, 8. So now the hydrogens are gone, but I have these 2 carbons that do not yet have an octet, so that makes me suspect a multiple bond. To get each carbon to have an octet, 4 bonds is what it wants, we'll need a triple bond. We formed 1, 2, 3, 4, 5. This is 2. How about another constitution isomer? Well, that is by simply moving the location of the triple bond. We put it between carbon 2 and 3. How about right at the start of the chain? So here's more hydrogen. This carbon has enough bonds already with 4. This one needs 2, this needs 2, and that needs 3 to complete the 4 bonds carbon requires. So we've created a structure that has 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, but we moved the location to number 1. So here we made 1. Those are 2 conjugal isomers, cyclopentene, that did not contain a ring. We just drew that. In benzene, we've talked about the aromatic structure of the alternating double single bond. Remember the term we use a double-headed aromatic structures. The case is one in which we draw a ring inside of that structure. That ring represents the delocalization of the pi bonds in each of the double bonds. The bonds are of equal length, which is the very definition of a resonance structure. Benzene is incredibly stable, simply due to the resonance of those alternating double bonds. Remind ourselves that it would be sp2 hybridized. You have equal electron density above and below the ringed structure. Delocalization of the pi bonds means it's that tweener length. So when I draw benzene and represent it like this, it's not that I have a true double bond here, and it's not that I have a true single bond here. The resonance structure provides equal length. The other bonds are equalized, spending an equal amount of time between all 6 carbons. Delocalized pi bonds. Cyclobutadiene. Cyclobutadiene. Cyclo means a structure that is in a cyclic circlet ring structure. But, 4 carbons. Buta, 4 carbons. Di means that there's 2 ene, 2 double bonds. Cyclobutadiene. 1, 2, 4 carbons in a cyclic structure. If it's like benzene, it alternates. We make double bond, single bond, double bond, single bond. So that's how it would be similar to benzene, alternating single double bonds. However, its bonds are not the same length. The double bond is actually shorter. I should have better representation. Double bond is shorter than the single bond. So it's not a square of equal length, but it's a where we have 2 separate bond lengths. Explain why it would be incorrect resonance structure. If it's a resonance structure, they're not the same. It's rectangular. And as soon as it told me that, I understand that this molecule does not exhibit resonance. It is incorrect to show a resonance structure. Benzene has equal bond lengths. Cyclobutadiene does not. They are not the same in terms of resonance. So it's actually very unstable due to the ring strain. And we'll learn that there's an anti-aromatic rule known as Huckel's rule at a later date. It might even be in, I think it is in the second half of the chapter, so it might be in the second chapter of the book, so it might be in Orgo number 2. So just remember, pi electrons that are localized, and therefore it's not considered aromatic. Delocalized exhibit the term aromatic exhibits resonance. Let's pause the video here, and we'll pick up with the next lesson called polar covalent bonds.